Welcome to Unit 7, Inference for Quantitative Data, with an emphasis on means. In this video, we're going to tackle topic 7.10, Selecting, Implementing, and Communicating Inference Procedures. To be honest, we're actually not going to learn anything new in this video at all over this topic 7.10. It's really more about kind of an overview, looking back at everything we've done and kind of putting it all together to really kind of honestly just take a step back and see how much work we have done over the last 2 units when it comes to statistical inference. So let's remind you guys what statistical inference is. It is the theory, methods, and practice of forming judgments about the parameters of a population and the reliability of statistical relationships, typically on the basis of random sampling. So there's a lot of, this is actually a really good definition of statistical inference here, but there's a lot of really good parts to this. And first off, I want to emphasize it is all about forming judgments about the parameters of a population. So let's talk about real quick what a parameter is. Now remember, a parameter is any value that comes, any value that comes from a population. And there's all kinds. There's the min, there's the max, there's Q1, Q3, the median, the mean, the standard deviation, a proportion. I mean, anything. There's tons and tons of them. But the 2 most famous that we've been focusing on a lot is all of Unit 6 was about population proportions. The proportion of a population is a parameter. For example, the proportion of people who are allergic to a specific allergen. And Unit 7 is all about population means. A population mean is also a parameter. It is the true mean of an entire population. For example, the true mean height of all giraffes. Now, to make these judgments about these population parameters, we need, the one thing we've taught you is that it's really hard because, populations are really massive. They're really big, and we can't get these values because there's so many objects or people or animals in that population. So what we have to do is we have to take a sample. So we take a sample proportion and we use that sample proportion to help us make a judgment about that population proportion. Or in Unit 7, we learned about how to take a sample mean and use that sample mean to make a judgment about a population mean. Now, this is all fine and dandy and it's all great, but it tends to look like we're using a single sample to make a judgment about an enormous population, and that's actually not true if you understand sampling distributions. Remember, the most important part of any statistical inference that we've done in the last 2 units is that a sampling distribution is always present. A sampling distribution is saying, hey, listen, let me think about what all samples look like. And then all sample statistics, right? So for example, all sample proportions, what do they all look like? And then I could see where mine fits in. And that way I could see if I'm really significantly high or low, or if I'm in the middle like everybody else. And the same thing for sample means. That's another statistic. And a sampling distribution doesn't show just one sample mean, it shows all of them. And then allowing us to consider what that sampling distribution looks like is how we could actually use a single sample to make a judgment about a population parameter. All right, so let's review really quickly what we learned back in Unit 6. Unit 6 was all about proportions, and we learned how we could take a sample proportion, which is a statistic because it comes from a sample, and use it to make some judgments about a population parameter. And we learned 4 different inference techniques. We learned a 1 sample z interval for a population proportion, a 1 sample z test for a population proportion, a 2 sample z interval for the difference between 2 population proportions, and a 2 sample z test for the difference between 2 population proportions. So we see the words interval and the words test here. Now I hope by now you know what those are. Remember, an interval is when you're simply looking for a population parameter. You have no idea what the population parameter is, so you would like to estimate it with an interval. So you find a sample statistic, whether it be a proportion or a mean, and you use that value, that sample, to form an interval for what you are, really confident that the true population value lies in. And then a test is when, somebody makes a claim. Somebody says, well, I think it's this, or I think it's that, or I think the true proportion of people that are blonde is more than 20% or less than 20%. Somebody makes a claim, and our job is to use a sample to try to show that there's evidence that that claim is true or lack of evidence. And again, I don't want to go over what all of that is because we've just spent 2 long units doing it. Now, Unit 7 was all about means. We learned how to do a one sample t-interval for a population mean, a one sample t-test for a population mean. We even learned one of those one sample paired t-tests, one of those special t-tests for the difference between pairs, two samples t-interval for the difference between two population means, and a two sample t-test for the difference between two population means. So the same idea, tests and intervals, and hopefully by now, again, we know what those are. So let's briefly review them real quick. Remember, an interval is that a problem that requires an interval is simply looking for a population parameter, either a proportion, a difference between two proportions, a mean, or a difference between two means. So the idea is that we don't know. There's no claim, there's no statement. We're just looking for what the population parameter could be. And there are 4 steps to an interval. I hope by now you know these steps. You have to name the interval and use context. So make sure you're saying, hey, this is a one sample z interval for the proportion of people that have blonde hair in the United States. Or this is a two sample t interval for the difference between the mean number of books students in Canada read and the mean number of books students in America read. You got to make sure you name it. Then you got to check the conditions, because even though we can't build the sampling distribution, and I hope you understand that, because remember, a sampling distribution requires that we know the truth. Even if we don't know the truth, we could still visualize what that sampling distribution looks like, because visualizing that sampling distribution, which allows us to say, hey, listen, I'm pretty confident that my sample is so close to the truth in the center that when I build my interval, I will capture that truth. And again, I don't want to explain all that because I've already done it twice now in both units 6 and 7. But go back and review that if you need to. But that is why sampling distributions are so important. And then we actually have to build the interval. If you remember the work, it's actually pretty easy. And then we have to interpret the interval in context. So that's all the fun stuff with intervals. Then we learned a lot about tests. A test is needed when a claim about a population parameter is made, and your job is to try to find statistically significant evidence that the claim is true. If you don't have enough evidence, we just don't have enough evidence to say that that claim is true. So here we have to give a name and give the hypothesis. We've practiced that a ton lately. You got to check the conditions and build the sampling distribution, assuming the null is true. Now here we could actually build that sampling distribution, because remember, we build that sampling distribution on the idea that the null hypothesis is true. And if we know that the null, or at least believe that the null hypothesis is true, then we could go ahead and build that sampling distribution. Then we could find the test statistic, either a z-score or a t-score, and the p-value of our sample statistic. And then we can make an appropriate conclusion based on our p-value. Again, I'm not going to reteach how to do all that. I've done it several times now, but that is how you conduct a test, whether it be for one proportion, one mean, or the difference between two proportions, or the difference between two means. Now, you need to know when to do what. So you need to be able to read a problem and understand, what do I have to do here? Now, there are usually multiple choice problems where a scenario is given and you simply have to select the name of the inference method required to solve. And there might be some more advanced free response questions where you actually have to not only name it, but then do all the work to actually answer the question. But regardless, what I'm trying to get at is that you need to be able to read a problem with no hints, no big title, hey, no flashing lights, this problem is about proportions. You need to be able to read a problem and know what to do. So let's make sure we understand how you do that. First off, you have to decide, do they want an interval or do they want a test? This is actually pretty easy. Because if a problem wants an interval, they will use the word interval. They will ask you to find an interval and they will give you a confidence level. So if a problem says something like, hey, find a 95% confidence interval for ... the mean height of kangaroos, well, then you know what you need to do. You got to find an interval. And it says mean. Oh, I got to find a interval for a mean. Now you kind of know what you need to do. If a test is what the problem requires, sometimes they might directly say, conduct a test, or sometimes they might simply say, hey, show me that there is significant evidence that kangaroos are taller than 8 feet. All right, well, if they're going to go ahead and do that, what they're looking for is a test. Because if they want you to show that there is significant evidence, the only way you could really show there is significant evidence, or lack thereof, is with a test. So let's look at several examples. We're actually going to look at 6 examples here. And if you want to pause the video and try to answer the question on your own before I go over the answer, that'd be a good idea. But we're going to look at 6 different scenarios, 6 different problems, and all we have to decipher is, what do I need to do? Do I need a test? Do I need an interval? Is it working with means? Is it working with proportions? What do I need to do? All right, here's the first example. Thomas believes that there is a significant difference between the mean time spent on homework between males and females at his school. So he plans to select a random sample of males and a random sample of females and find the mean of each group to compare. Which of the following is the most appropriate test to investigate? All right, so the first thing I noticed is that they clearly don't want an interval. They want a test. It actually says appropriate test. So I need a test. So now I have to figure out, all right, is this a 1 sample test or a 2 sample test? Well, he clearly is making a comparison about the difference between males and females. The fact that there are 2 very clear populations here, males and females, tells me that this is a 2 sample test. So anything with 1, I'm going to go ahead and cross out. Can't be right. Now the next question is, am I looking at the difference of proportions or the difference of means? Well, let's look. Oh, what do you know? It actually uses the word mean. He wants to look at the difference between the mean time spent on homework. He doesn't want to look at the proportion of anything. He's saying mean. So he wants to know, hey, or actually he believes that there is a significant difference. Well, if I want to prove there's a significant difference, I'm going to need a 2 sample t-test for the difference between means. So what he's going to do here is he's going to get a sample mean of females, maybe the average amount of time they spent on homework, a sample mean for males, and he's going to conduct a test to determine if the difference is so significant that he could say, oh, males spend more time or females spend more time, whatever more specifics of the problem can be. All right, let's look at example 2 here. A National Pet Association claims that 17% of all dogs are malnourished. The mayor of a large city wants to see if the proportion of dogs in his city that are malnourished is less than 17%. So if a large sample were taken, which of the following is the most appropriate test to investigate the mayor's belief? All right, so first off, am I working with 1 sample or 2 sample? Well, it seems like I'm only working with 1 sample. It just says if a large sample. I'm only concerned with dogs. It's not like I'm looking at dogs versus cats or 2 different species of dogs. I'm only looking at 1. So this is looking to be a 1 sample test. Now, it never asks for an interval. In fact, they want me to investigate his claim. He's claiming that the proportion is less than 17% in his city, so he wants to try to prove that. The only way you could prove a claim is true is with a test. So this is clearly a test, and even all the options are tests as well. Now, is this means or is this proportions? Well, the big hint is percentages. Percentages are proportions. 17% of dogs are malnourished. Is a dog malnourished? Is a yes or a no question, right? This isn't a mean. This isn't something that you could put a unit on, right? Yes, no. Yes, malnourished, no. That's categorical data. Categorical data, we use proportions. So that is a clear sign that this is a 1 sample Z test for a population proportion. So he wants to show that the proportion of dogs in his city is less than 17%. Okay, so he's going to go ahead and get a sample of dogs. He's going to find the proportion. Hopefully it's less than 17%, or he should probably just stop now. And then he's going to conduct a test to try to prove that it is significantly less than 17%. All right, example 3. For a random sample of 80 people, times were measured to complete a puzzle with 8 hours of sleep and with 3 hours of sleep. A coin was flipped to determine what each subject did first. Solve the puzzle with 8 hours of sleep or on a day with 3 hours of sleep. The researchers' belief is that a subject can solve a puzzle faster on more sleep. Which of the following is the most appropriate test to investigate their belief? All right. So, first off, this is again a test. They never ask for an interval. They want me to actually show that there is significant inference. And this guy has a claim. The researcher's claim is that you could solve a puzzle faster on more sleep. So, this is going to be a test. It says appropriate test. All right, now, is this means or is this proportions? Well, I don't see any percentages. I don't see the word proportion. They want me to look at the time. This is the time to complete a test. Time is something that is measurable. That means it's quantitative. Quantitative means we're working with means because I want to show that the average time to complete a puzzle, if you have more sleep, is faster than if you have less sleep. So this is clearly a problem with means. So any problem with proportions, I can immediately wipe out. Now, it does say that there's one sample of 80 people, but notice they actually got measured twice. All 80 people did the puzzle with 8 hours of sleep and with 3 hours of sleep. Now, they did flip a coin to determine what they did first. Did they do the puzzle with 8 hours or 3 hours? And then they switched, a couple days later. But this is a clear sign of that special scenario, a one sample paired t-test, because we have 80 subjects that we measured twice. How long did each person take to solve a puzzle with 8 hours? And how long did they solve the puzzle with 3 hours? So we want to look at the difference. We want to show that there is clearly faster to solve the puzzle on 8 hours of sleep than it is with 3 hours of sleep, okay? So this is where we're doing that one sample paired test. So we're gonna have a bunch of times on 8 hours, a bunch of times with 3 hours, and actually all we really care about is the differences between those times because we only had one sample of 80 people that got measured twice. So this is that special paired t-test. And again, I will say that the majority of times on an AP test, when they do one of these questions about picking what test to use, I don't want to tell you to always pick the paired t-test, but I will say a lot of times the question is a paired t-test because that's something that kids sometimes struggle to identify. So being able to identify it is super important. All right, example 4 is an arborist. It's a person who deals with trees. So an arborist wanted to estimate the mean surface area of leaves on a large maple tree. She selected a random sample of 10 leaves and found the mean and standard deviation of the surface areas. Which of the following is the most appropriate way to investigate this? Now, notice that there's no claim being made here. She just wants to estimate the mean surface area of the leaves. She has no idea what it is. She's not believing it's more than this or less than that. She just wants to find it. That's where you're going to need an interval. Now, all of our choices involve an interval here, so that's pretty obvious. But if she wants to estimate something, you need to do it with an interval. Now, is this 2 samples or 1 sample? Well, it says she selects a random sample of 10 leaves, and she finds the mean and the standard deviation of those 10 leaves. Okay, that sounds like there's only 1 sample. It's not like she's comparing maple leaves to ash tree leaves or this, leaves in North America versus leaves in South America, right? There's not 2 populations here. There's only 1. So anything with 2, I can get rid of choices C, D, and E there. Now, is this means or proportions? Well, I've used the word mean several times now. In fact, we see the word mean. So this is clearly a 1 sample t interval for a population mean. She's going to take her 1 sample, she's going to add, she's going to subtract a margin of error. Sorry for my messy handwriting. And she's going to get an interval that she feels will estimate the surface area of the leaves. All right, example 5. A new fitness program promises to significantly reduce your body fat percentage after just 2 months. To test this claim, a researcher gets 10 volunteers to participate in the fitness program. The volunteers have their body fat measured at the beginning of the study and at the end of the study. Which of the following is the most appropriate test to investigate this claim? So this is a test, and they want to see if they can significantly reduce your body fat percentage after just 2 months. So this is clearly a problem that works with means because, we're not just saying, did you lose body weight? Yes or no, which would be categorical. We're actually going to measure. Body fat is something that you can measure and show that it went down. So this is clearly working with means. Now, if you really take the time to read this problem, you'll notice one more time, this is one of our paired t-tests, right? Threw another one at you here because I know how often these come up. So there was only 10 volunteers, but they were measured twice. They were measured at the beginning of the study and they were measured at the end of the study. So I don't really care what your body fat was at the beginning. I don't care what your body fat was at the end. I simply care about the differences because I want to show that you can reduce your body fat with this new program. All right, last example here. A researcher is interested in determining, if the proportion of African Americans that test positive for COVID-19 is larger than the proportion of white Americans that test positive for COVID-19. She plans to select large samples from each population to find out. To investigate this, what type of test would be most appropriate? All right, so we clearly are looking at two different proportions or populations, right? We're clearly looking at African Americans versus white Americans. So we're definitely going to take a sample from each. It even said select large samples from each population, clearly telling that there are two populations here, two samples here. Now, am I working with means or am I working with proportions? Oh, what do you notice? It uses the word proportion. Do you have COVID-19? That's a yes or that's a no. That's a positive or that's a negative. That's going to be categorical. Measuring COVID-19 is not something that you measure with a number. You measure it with a yes or a no, a positive or a negative. So this is clearly working with proportions. And heck, it even says the word. So this is a two-sample z-test for the difference of proportions. All right? So make sure that you know how to read a scenario and know what to do. Okay? Now, just identifying what to do is awesome, but then you have to know actually how to do it. So you got to know how to go through all the steps. And that comes with practice and studying. All right, let's talk about conditions, because I cannot tell you how many times these conditions get overlooked, and a lot of kids just kind of brush them off as meaningless, and it actually costs you a lot of points on the AP stats test if you do that. So understand that in all situations, intervals or tests, with any parameter, proportions or means, the conditions are necessary to have the sampling distribution so that we could understand how our sample statistic fits into all possible sample statistics. So each condition is essential to building that sampling distribution. So if you're ever asked, why are the conditions so important? It's because of the sampling distribution. You need the conditions. That way you could build the sampling distribution appropriately. That way you could really make that judgment about the population parameter. All right, inference is done with considering random sampling, right? All inference is about random sampling, so a sampling distribution has to be needed. Now, remember, a distribution involves three things. This actually goes all the way back to Unit 1. When you look at a distribution, you got to talk about the center of that distribution, the spread of that distribution, and the shape of that distribution. And all three of our conditions are attached to those three items. Condition 1 is attached to the center. When sampling from a population, the sample must be selected randomly in order to avoid any bias. That's our first condition. But that condition directly ties to the center. We need the true population parameter, whether it be a mean or a proportion, to be in the center of the sampling distribution. And this will only happen if we can assume that the samples are selected randomly. So remember, there's actually several different centers here. This is the mean of all possible proportions. So if you are going to be looking for the true proportion, it will be in the center because it is the mean of all sample proportions. Here is the mean of all sample means. And the true mean of the population will be in the center because that is the mean of all sample means. Even when we're doing that paired test, the mean of all differences will be smack dab in the middle because it is the mean of all sample difference means, okay? And here is looking at the difference between two proportions, and the true difference between two proportions will be in the center. Why? Because it's the mean of all possible sample differences. Same thing for here. We're looking at the difference between two means, and the true difference between two means will always be in the center because it's the mean of all possible differences. Okay, so now there is one little thing here. When performing an experiment with volunteers as subjects, which subjects receive what treatments must be done randomly to avoid bias. So when you are selecting people randomly from a population, you need to select them randomly, right, to avoid bias. But in an experiment, this condition is actually a little different because in an experiment, you're not selecting people from a population, you're assigning them treatments. So the randomness comes through what treatments you assign them must be random. So what people get pill A versus what people get pill B, that has to be random. All right, let's talk about spread because that is why we need condition 2. Condition 2 says when selecting samples randomly from a population, we need those samples to be independent of each other. Well, when we sample with replacement or without replacement, independence is actually not true. Because if you don't replace the people you just sampled back into the population before you take another sample, you have actually changed the population because you've left those original people out. But remember, the rule says as long as our sample is less than 10% of the population, we can assume independence is still okay because the slight change is negligible. We just don't worry about it. That's why the second condition is called the 10% condition. We need our sample to be under 10% of the population to assume independence. And if we can assume independence, we could calculate standard deviation, or typically we have to calculate standard error. And that's totally okay, and that's awesome. There's one big kind of note here. A lot of kids forget about this, and that is if you're performing an experiment where you're using volunteers as subjects and the subjects are randomly placed into treatment groups, we actually don't need the 10% condition. Because in an experiment, again, you're not sampling randomly. You're not picking people from a population. In an experiment, you have your 50 volunteers, 25 get this, 25 get that. So you don't actually have to check the 10% condition only in an experiment, again, because you're not selecting people from a population. All right, and the third condition is always important, and that is the shape. We want that shape to be normal, or when you're working with means, we need to use a t-distribution, which is pretty close to normal. Now, this condition will only be true if you're big enough. So the generic third condition is called big enough. Some people call it the large counts condition. We simply need our sample to be big enough. Now, how do we know our sample is big enough? Well, we'll get there in 1 second, but why? Why do we need our sample to be big enough? Because we need the sampling distribution to be normal, or at least a t-model. Remember, p-values cannot be found if you're not normal. We need normal CDF to find p-values, or t-CDF. If we're not normal, if we're not a t-model, we cannot find p-values. So the big enough condition is so important because we need that shape to be normal, or we need it to be a t-model if we're working with means. So how do you know you're big enough? Well, when you're working with proportions, you need 10 or more successes and 10 or more failures in your sample. So that's where we actually have to check n times p and n times 1 minus p, because we have to make sure that we do have 10 or more successes and 10 or more failures. And as long as you got 10 or more successes, 10 or more failures in your sample, you are big enough. That's for proportions. That was unit 6. In unit 7, remember, to be big enough when you're working with means, you need your sample size to be 30 or larger. That makes it really nice. Or, don't forget, we've gone over this several times, if your sample is less than 30, you are still okay to proceed with a t-model as long as your data has no major outliers or major skewness. All right, so now that we've gone over the conditions, and again, I can't tell you how many times I've seen AP questions that ask you about a condition, and they'll say, hey, is this condition true? And more importantly, why? Why does it need to be true? So make sure you know how to answer that when you're talking about condition 1 for the center, because that's where the truth is, in the center, and the truth is only going to be in the center for random. Spread, we need that 10% condition to be met, that way we can assume independence. And then the shape, we need to use that normal model or that t-model, and we have to be big enough to know that. All right, a couple other big questions that come up are errors, and this could be applied to proportions or means. So let's just briefly, I know I've gone over these several times, just briefly just put them on here, that way you can review them. A type 1 error is when the null hypothesis is true, but the error is we believe we have the evidence to reject it and claim the alternative is true. So we think the alternative is true, when it's really not. And a type 2 error, the alternative hypothesis is true, but the error is we did not find enough evidence to conclude the alternative is true, hence we fail to reject the null, which is false. So type 2 error is the alternative is true, but we keep the null. We don't think the alternative is true when it really is, okay? And one more comment here I want to talk is about power. Every now and then on the AP test, power comes up, and power is a super important concept that, again, that can be applied to proportions or means. Power is the probability that we reject a null hypothesis that is false and find enough evidence to show the alternative is true. So if the null really is false, we want to conclude that, so we want to show the alternative is true. And the big question is, how do you get more power? There's 2 ways to get more power. Get a bigger sample size. Remember, a bigger sample size is always going to reveal the truth better. So a bigger sample size 500 versus 1,000 versus 2,000, a bigger sample size is always going to be a better reflection of the population. So if the alternative is really true, a bigger sample should always help you see that. The second thing is the further the true population parameter is from the null hypothesis, the more power you will have. Now you got to really think about this. For some kids, this is hard to understand, but if the alternative is true and we want to conclude that, a population parameter way far from the null will make it easier to show that the alternative is true. Now this can be a little bit tricky, so let me explain this with two different problems. So right here we have a problem dealing with a test for a proportion. So the null is that the proportion is 23% and the alternative is we believe it's less. So the idea is this: if the alternative is really true and I want to reject the null and take on that alternative, if the truth is 22%, hey, the alternative is true. 22% is less than 23%. But the point I'm trying to make is that might be hard to see because 22 is only a little bit less than 23%. But if the truth is something like 8%, way far away from the null, then it's going to be easier for me to see that and conclude that the alternative is true. Same thing here. Here's a test for a population mean. The null is that the mean is 20, and the alternative is that the mean is greater than 20. Again, if the alternative is really true, and the mean is, say, 22, well, okay, 22 is greater than 20, but it's just a little bit greater, so I might have a hard time seeing that. But if the mean is 40, right, something way above 20, well, then if the mean really is 40, and I get a sample, well, the sample should show me that, right? The sample should show me that it's way more than 20, hence allowing me to reject the null and go with the alternative. So two ways to get more power: bigger sample size, and if the true parameter is further from the null, then it should be easier for me to see that. All right, guys, that's it for 710. You remember the whole idea here is just making sure that you understand all of the different inference procedures that we have learned with proportions and for means, and being able to really understand when to do what and why all the pieces and parts are super important.